All right, first, a quick review of some things we already know and sort of justification as to why we need to do what we're about to do with calculus. So first of all, we know that if something is moving at a constant velocity, we would expect its position graph to look something like this. Now, it might not be exactly this position on the graph, it might point up, or it might start at a different location on the axis or something, but it's going to be some sort of a straight diagonal line. And we also know that if it's a constant velocity, that if we were to look at the velocity graph, we expect to see something that looks like this. For my particular graph, we expect to see a horizontal line. We've also learned that the slope of this graph tells us the value of this graph. We've made those sorts of connections from earlier classes. And we've also learned that if we look at the velocity graph, we could find the area of this shape, this rectangle, and the area would tell us the displacement. Okay, so these are all sort of facts that we used in the first time through physics, our first year class. We also had a formula that we could say that position was velocity times time. Okay, now what's kind of restricting about all these things is the fact that since it's at constant velocity, it meant that all of the forces completely balanced out, and of course there was no acceleration. And that's just not the way things always are. Now, then we looked at situations where there was acceleration and where we had our position graphs were some sort of a curve. Okay, and again, I'm just drawing a particular one. It could curve down, it could curve up at a faster rate, it could start at a different location, a different initial position. Okay, but it was some sort of a curve. And then when we looked at the, that's an X, when we looked at the velocity graphs for that same motion, we saw a diagonal line. So these were the patterns that we saw, but it was still the same sort of thing where the slope told us how fast it was going. It was just that we had to look at particular moments in time because the slope changed, and so the velocity changed. And so there wasn't just a single value, so we came up with a formula that described how the velocity changed with time. We also had a formula that described the positions. We had this basic formula here, v sub ot, plus 1/2 at squared. Okay, that was kind of our basics. So we had this going on here, and this allowed us to handle more situations. Now we could handle situations where there was an unbalanced force, when there was a net force that was non-zero, and so there was acceleration. But we actually always assumed, it might not have been obvious to you, but we always assumed that these forces were constant for a particular situation. The force did not change as time went on or as the position changed. And that's, again, a good approximation for some situations, but there are places where this doesn't work. And so that's what calculus allows us to do. It allows us to handle situations that we just can't handle with these sorts of formulas. There's another level that we need to go to. So what happens if we have a non-uniform or a non-constant acceleration? What happens if our forces are not constant values of force? If we don't just have a formula that always works for a particular situation? Well, first of all, what would happen is that our velocity graph would no longer be a straight line. not a horizontal line, not a diagonal line. It would be some sort of a curve. Okay, and if that is some sort of a curve, then this position graph would have to be something even more complex. It can't just be a nice simple quadratic curve. It would have to be something, I don't know, something kind of crazy, maybe something like this. Okay, so how do you deal with those sorts of things? Our formulas that we had before, they were based on quadratic things and linear things. And now we've got this different situation. And that's where calculus comes in. Calculus is going to allow us to look at a velocity graph and be able to predict what the position graph would look like. So it's going to allow us to do something like this, where if we know that the position graph has some sort of crazy shape to it, we are going to be able to predict what the velocity graph would look like. Okay, and I can't do that just very easily by looking at it. What we need is some sort of a formula that describes what this position looks like. And it's going to be something x as a function of time. And it might be something crazy looking. It might be like 1.2 t cubed minus 0.6 t. Okay, it's not going to look like the same sort of dimensions, the same sort of degree of our other formulas. But if we can describe the way the position changes with some sort of function, we're going to be able to determine from that another formula, another function that tells us how fast it's going from it. That's what calculus does for us. It also allows us to do the opposite, just to say, oh, I have this velocity graph that is some sort of a shape. Can I predict what the position graph looks like? Yes. Okay, and in fact, we can start with an acceleration and we can predict from that acceleration what the velocity would be, what the position function would be. Okay, so it's going to be a very useful set of skills for handling situations beyond sort of the ideal, always works out kind of things in physics.